easier because I'm leaving town in a couple days, so I'm kind of glad to be home. Anyway, this talk is about, basically it's a broad brush look at the Pacific Northwest that came out of those roadside geology books. And I'll refer to them a few times in there. One of the kind of fun things about the Washington book was my co-author, Daryl Cowan, was both my master's and my PhD advisor at the University of Washington. So it was great to be able to, that was a long time ago, I think. and to still be in touch like this and to share that was a really wonderful thing, I think, for us both. So can I share the screen? Do I have that? Oh, yes. Okay, great. So here's the talk. It's called Assembling the Northwest. And these are mostly observations and things you can see from the highways and things like that. So we'll get right to it. Okay, so I guess y'all have noticed that we've got some beautiful places here in the Pacific Northwest. This is on the Oregon coast, near the town of Bandon, where you've got all these amazing sea stacks. There's the Cascade volcanoes. This is looking over Mount St. Helens towards Mount Rainier. If in Oregon, there's the Sisters. I mean, the Cascades go from southern British Columbia or near Vancouver at Mount Garibaldi all the way down to Lassen Peak in Northern California. So there's a whole bunch of volcanoes in Oregon. And in the North Cascades.
Bye.
Is everything okay? Oh, okay. Sorry, I just thought somebody had a question or something. Anyway, if you go up to the northern Washington, you've got the North Cascades, which are not, except for a couple of volcanoes, the range as a whole are these, deep-seated igneous and metamorphic rocks that have been exhumed and are being eroded by glaciers. If you go east of the Cascades axis, you get in the much drier climate like where you all are in the Tri-Cities. This is looking down into the Yakima Valley. And in Oregon, we've got, you get actually down into the Basin and Range Province, the Great Basin. This is Lake Abert. You can see as as the water is evaporating, it's leaving behind this crust of salts. And here's just a physiographic map of the whole region. And you can see that it's how variable it is. And very conveniently, that physiography falls out into these different provinces, if you will, which was made the structure of these roadside books really quite easy, where each physiographic province formed its own chapter. And so we could write an introduction to the chapter, and then the road guides would follow that introduction within whatever province they were in. But that's the physiography. But as it turns out, it's very closely related to the geology. Here's a geologic cross-section across the region from the subducting Juan-Fuca Plate and the Olympic Mountains across the Cascades, and then over all the way to the boundary between Idaho and Washington. And so the cross-section, it's pretty complicated, but the point here is that my talk is what I want you to do is focus on this heavy dashed red line, because that separates the basement rock down below from the cover sequence. And that's pretty much how the talk is going to be constructed. I'll first skip around some of the things down in the basement, and then I'll talk about the cover. But before I move on, I just want to make sure everybody is on the same page when it comes to talking about plate tectonics, because the plate movements are so critical to the geology of the Pacific Northwest that I just want to make sure everybody's there. And so if you're not familiar with plate tectonics, the idea is that the Earth's outer shell, called the lithosphere, is broken into these gigantic fragments called plates. And as they move around, they cause earthquakes, or they cause volcanic activity, they cause mountain building. And so each of the different colors here represents a different plate. And you can see in the Pacific Northwest, we've got 3 plates. We've got the Pacific plate in yellow, and the Juan de Fuca plate, the small one here in blue, and then the North American plate in brown. And so the next slide will be a close-up of that area. So here's the Pacific plate now in gray, and the Juan de Fuca plate in light blue. And then starting at this line here, we've got the North American plate. And you can see the Cascade volcanoes are parallel to that line. And what's happening is that the Juan de Fuca plate here is pulling away from the Pacific plate, and it's sinking right here at what's called the Cascadia subduction zone, and it's going underneath North America. So in a block diagram kind of way, it would look something like this, where here's the Juan de Fuca plate pulling away from the Pacific plate and sinking. And as it does, it heats up, and that causes it to dehydrate, which causes water then to rise into this overlying North American plate, which causes melting. And that melting then, that's liquid rock, which is magma, and it rises and it fuels the volcanoes, which is why these volcanoes are all parallel to the subduction zone. So the Cascade volcanoes start here at Lassen Peak and go all the way up into southern BC. Okay, well, that's today. But this subduction has been going on for a long time in the Pacific Northwest. You can look at the Cascade volcanoes today. They form this chain. But if you think about it, they're being fed by magma from below, and not all that magma makes it up to the surface to erupt. A lot of it stays underneath the ground, and it cools and it crystallizes there. And so it turns into an intrusive igneous rock. And probably the best known of those is granite, which you can see down here. This is actually some exposed granite near Mount Rainier. And throughout the Oregon, Washington, there are granites that are related to subduction that are 80 million years old, 100 million years old, 140 million years old. So this subduction has been going on a long time. It's also really important because the movement of plates explains how the continent grows, and that's really relevant to Oregon, Washington. It's this process of continental accretion. And you can imagine here, like in this diagram on the right, you've got your subducting plate, and if it's got a topographically high area, like an oceanic plateau or island arc or something, and it as it comes into the subduction zone, it's going to jam it up, and that can cause subduction to stop. But the two plates are still converging on each other, and eventually it's going to break again farther offshore and continue the subduction. But in the process, it causes this high area basically to get added on or accreted onto the continent. So if you look at that cross section again, you can see that the basement rock here are these big, they're called accreted terrains. They're big blocks of Earth's lithosphere that has been added onto the edge of the continent through time. First, this one Q for Quinella, and then terrains of the North Cascades, and then this last one, Silesia. Here's the edge of North America about 250 million years ago. And then on top of that, the cover either erupted as volcanic rocks or sedimentary rocks or so on. Now this is a cross section across Washington, and you can see here's one across Oregon, and it's pretty similar. There are still accreted terrains. There's some different terrains. It's not all the same, but still accreted terrains making up the basement. And then there's a cover sequence above, and there's a lot of similarities in the cover sequence, and there's also a lot of differences. So I'm going to start here talking about Silesia, which was the most recently accreted terrain. You can see it's also really big, and it's in both Oregon and Washington. And Silesia was a big oceanic plateau. And we know that because, well, we can tell that a lot of it was erupted underwater, because when you see rocks of Silesia, many of them, not all, but many of them they form these pillow shapes. It's pillow basalt. So when basalt erupts underwater, it forms these rounded blobs. And that's because you can imagine an eruption of basalt coming out into the seawater, where you get like a bleb of basalt erupted, and it's going to cool very quickly around the edges where the seawater is cold, but it's going to stay hot in the inside and malleable. So it sinks down, lands on the seafloor, and then another blob lands on top of it, and then another blob on top of it. So they all kind of conform to each other's shapes, and you get a whole pile of these things. I'm not sure why it skips back and forth like that, but and so anyway, if you look at a geologic map of Oregon and Washington, this is the coast range. And wherever you see purple here, starting at Roseburg, going all the way up, you see all the purple. This is all Silesia that's exposed. And that's the basement of the coast range. And here's another view of some of it. This is behind Corvallis at Mary's Peak. It was accreted, added to the edge of the continent 51 to 49 million years ago. And then after it was accreted, more rock either erupted or was deposited over the top. So this is actually the Tyee Formation. But that younger cover rock then are all the other colors here except for the purple. So if you were to drill a well, say right here in this lime green stuff, you would go through the cover sequence and then down into Silesia. And so it's this huge province. It goes all the way up from Roseburg to the northern tip of the Olympic Peninsula, actually onto southern Vancouver Island. A really good place to see it is if you go to the Olympic National Park. This is the Hurricane Ridge Road, and here that's this road right here. And you can see it crosses this sort of horseshoe shape purple zone. So this is all Silesia where it's exposed. So you drive right across, right through here, and you can see all the pillows in the road cut. And there's lots of pullouts. You can get out, you can pet the pillows, go see them and look at different features and things like that. And then continue on to the top of Hurricane Ridge and get a fabulous view. You can see Mount Olympus and what's called the core of the Olympics. And so here's Mount Olympus in this core, and that is all part of what's called the Olympic Subduction Complex. And so Silesia has been pushed up over that along this fault zone here called the Hurricane Ridge Fault. Now, if you look at the rocks of the Olympic Subduction Complex, you can see just how variable they are. And you can imagine this, like it's stuff getting put into a subduction zone through time is going to be super variable, and it's going to be highly deformed because you're always having this plate sliding underneath, all these faults forming and everything. And so up here at the Hurricane Ridge Road, you see that the rocks are actually low-grade metamorphic rocks. But if you drive down to the coast, you can see more recently deposited rock of the Olympic Subduction Complex, and you can see just how variable it is. This is its second beach. I mean, there's it's just a beautiful area. There's so many cool coastal features and everything. But if you look at the rocks, you can see like these rocks here it's a fragmental rock. It's a breccia. It's part of a submarine debris flow. But here in the middle, there's this chunk of limestone. All this other stuff is sandstone. And you're kind of wondering, like, how did this happen? But it gets mixed up in these submarine debris flows. But you see these fragmental rocks, and you also, at other places, see really what look like pretty nicely behaved sandstones and shales and stuff. And so these rocks, you can see, are tilted. But if you actually take a close look at them, You can see the graded beds indicate, you can see here it's pretty coarse grain. It gets finer and finer grain. Here's the base of another coarse bed, and it gets finer and finer upwards. So it's going younger as you're going downwards. So these rocks have been completely overturned. And if you go around the corner, you can see just how incredibly deformed some of them are as well. There's a fault right along here. This is about 6 feet high. I'm not sure there's actually a good scale in this photo, but you can see a fault here, and then you can see these rocks are all folded up above it. So definitely rocks, highly deformed and really variable down at the coast. Now here's a map showing accreted terrains in North America, all the different colors. The gray represents Paleozoic North America before those terrains were added on. You can see where the Olympic Subduction Complex is here. You can see Silesia, the extent of that. And you can see Oregon, Washington. You can see that the edge of North America just clips the very northeastern corner of Washington. But it raises the issue, how do you know when you're on an accreted terrain or when you're on ancient North America? Well, a lot of times you can't tell because you're up in the cover, and that was clearly formed on North America on top of the accreted terrains. But if you go onto what is North America, there's certainly a very defining, clear characteristic of North America. And as an example of that, here's the Grand Canyon. And in the Grand Canyon, you've got this ancient basement, okay? But on top of it, you've got Cambrian age sandstone, shale, and limestone. So 500 million years old sandstone, shale, limestone that represents the ocean transgressing or moving up onto the continent of North America. And you see this all over North America. You see it in the Grand Canyon here where the star is. You see it in Montana. You see it, I taught for 3 years in Eau Claire, Wisconsin a long time ago. You saw it in Wisconsin. And but you don't see it in the accreted terrains, and that's because the accreted terrains weren't part of North America. They don't have the same sequence of rock. But if you go to northeastern Washington, you can see that. And I like this picture because it's called Sweet Creek Falls. It's up in northeastern Washington. And every time I went here, it was such a great respite from the heat. It was really hot when I had been up in this area. Multnomah Falls, beautiful area, but boy, it got really hot. And you could just park the car and walk less than a quarter mile and you were here. It was nice and cool. There was water. And then you get these cobbles of quartzite. And these, quartzite is metamorphosed sandstone. And this is called the Addy quartzite. It's Cambrian in age. And you can see it washed down from farther upstream. On top of where this outcrops, you see Cambrian shale, and above that you see Cambrian limestone. And then stratigraphically above that are these rocks, which is the Ledbetter slate. It's an Ordovician age shale that was metamorphosed into slate. And so you've got that sequence of North American rock of Paleozoic age in the very northeastern part of Washington. And that is right up in this area. And I liked showing this Highway 20 because it was, I think, one of the most amazing roads in the whole state of Washington. And we really enjoyed writing about it. Because if you can start here on North America and you can go west on US 20 or Washington State 20, and you cross the large accreted terrain of Quinella and see these rocks. Then you cross the North Cascades, or multiple accreted terrains in the North Cascades. And then you can take a ferry back across onto the Olympic Peninsula, and there you are on Silesia. So just on Washington State 20, you can start in North America and just go across all these accreted terrains and see the the whole gamut of the basement in Washington State. To talk about the cover, I like to talk about the Columbia Gorge and do it kind of as a field trip from Portland up to the Dalles. And there, I like it partly because the gorge is shared by both Oregon and Washington. It also makes for a really great field trip where you can drive up Interstate 84 and then come down Washington 14 or do it in the other direction. And here are two maps. One, the northern one in Washington, is one of the road guides in the Roadside Geology of Washington. The southerly map is for the road guide of I-84 in Oregon. And you can see there's all these cool places that point out where you can see things. But it just kind of gives an idea of the geology. Now remember, these are two maps. The river is not this wide. This is actually the river. That's, they're just two maps stuck side by side. And you see a variety of rocks as, you just look at the maps, you can see all the different colors. These are I tried to simplify things here. In yellow, basically, you've got these landslides and rivers and flood sediments. Cascade range, basalts and andesites in pink, including Mount Hood, which is right about here. You have these things called the boring volcanics, which are this sort of maroon or magenta color. I'm not sure what color that is actually. The so-called Troutdale Formation in green. There's even some granitic rocks, and then lots of Columbia River basalt, which I probably don't need to be telling you all a whole lot about Columbia River basalt. And then there's also earlier volcanic rocks of the Cascades. So it's complicated. There's a lot of stuff in the gorge, but one of the things I want to point out is it's all cover rock. You don't see any basement. And the main points I want to make is that in the Columbia Gorge, we see volcanic activity that basically dates back to the early Cascade Range, which was on the order of about 40 million years ago. We see that the Columbia River itself dates back at least 12 million years, and there's evidence actually that it goes back considerably farther than that. We see that the structure of the bedrock really controls the shape of the gorge, and there's lots of stuff about Ice Age floods there. It's not quite what it is up in your country, but there's some pretty cool Ice Age flood stuff in the gorge and even farther to the south. So let me kind of start this field trip here. You can either drive east on 84 or east on Washington 14. You can see there's a completely different experience depending on which way you choose to go. I-84 is fast and pretty furious. Washington 14 is a lot more pleasant. And you can see a lot of the same things. And what I want to point out here is, okay, there's Mount Hood. You can see the active Cascade stuff. But also what I'm really pointing out here is this mountain here. This is called Larch Mountain, and it's in both photos. And it's part of what's called the boring volcanics, which are not boring at all. They're named for the town of Boring, which is right here in the Portland area. And Boring, the town of Boring is, it's a pretty nice town. They've got a little bakery and they have a sister city in Scotland named Dull. So they take pride in their name, I guess. But the volcanics around there, they're named for the town of Boring. So the Boring volcanics, you can see all the different colors here. These correspond to different ages. So they range in age from about 3 million years ago to younger than 500,000 years ago. And they get as young as 56,000 years. And so they're a really important feature in the Portland area. And they actually form many of the hills and buttes around Portland are either cored or made up entirely of the Boring volcanics. And they're unusual because they're they're west of the Cascade axis. So if you look at this block diagram again, the boring volcanics are right here, and it's hard to understand why they're there, because you need this subducting plate to reach a certain depth to be hot enough to drive off the water that causes the melting, and the plate is not as deep. And so there's a lot of different ideas about why the boring volcanics might be there. Some people think it's because of rotation in this area, which might cause some local rifting that allows material to come up more easily. And so aside from them being a bit of an enigma, they're also considered a hazard because, the most recent might be 56,000 years old, and that's this one right here, Beacon Rock. But they're really voluminous. There's been a lot of activity in the last 3 million years, and 56,000 years geologically doesn't mean that it's over. I mean, there could be a hiatus of 56,000 years and it could start to erupt again. So it's in an urban setting, and it's definitely a subject of a lot of interest amongst a lot of people. But if you go up the river, you can see Beacon Rock. This is Beacon Rock here, which is an eroded neck of one of the boring volcanics, and it's only 56,000 years old. But the hills behind it are older volcanic rock, and much of them consist actually of the Columbia River Basalt group, which, like I said, I'm sure you're all really familiar with. I'm continually fascinated by it. Especially in the gorge, you get such great, amazing, continuous exposures of it. And you can look at individual flows for such a great distance. It covers this huge area of southern Washington and northern Oregon. It's related to the Yellowstone hotspot. These things originated in eastern Washington and Oregon and flowed all the way to the ocean. They're just amazingly voluminous. This is an area of over 77,000 square miles with a volume of more than 50,000 cubic miles. And it's kind of hard to imagine how much that is. But one way I like to think of it is in the Grand Canyon, the National Park Service estimated the volume of air in the Grand Canyon to be about 1,000 cubic miles. So the volume of the Columbia River Basalt Group is more than 50 times the volume of the air in the Grand Canyon. 94% of this erupted by 14.5 million years ago. So something like 48,000 cubic miles erupted in a period of just 2.5 million years. So really voluminous, and it followed the path all the way to the Columbia River, to the coast. Multnomah Falls is a kind of a fun place to see it. There's several individual flows of the Grand Ronde basalt here, which is the main part of the Columbia River basalt. If you look at this upper flow up here, it looks kind of hackly, and up close you can see that it's got all these pillow shapes. So these are lavas that flowed into a lake. There were apparently a lot of lakes along the path of the Columbia River basalts as they were flowing on their way to the ocean. And here's an exposure right at the Dalles. If you're driving through there, it's less than 5 minutes off the interstate, where you can see these pillows, and they basically grade up into this colonnade up here. So this is one flow. So the idea is that the flow poured into a lake, forming all these pillows, but it gradually filled up the lake, and then the flow continued over the top of that as a subaerial flow, forming the colonnade. And this is a view of a place called Mitchell Point, which I like. This is kind of a crummy photo, but I like it because I took it out of my car window and it shows the milepost. in these books, the roadside books, we're really careful to include mileposts so people know where to see things. Because it would always drive me crazy when people say, yeah, you know, on your way to the Dells, you can see this. And it's like, well, where do we look? But this is Mitchell Point, and it's actually a really important place as far as the age of the Columbia River. And it's one of the places I highlighted in my new book called Oregon Rocks. And here's a better view, a better picture of it. This is from the Oregon side. And you can see the rocks are tilted to the south. And the lower ledges here, this is Grand Ronde basalt. And up at the top is the Saddle Mountains basalt. That's the Pomona member is 12 million years old. But you'll notice here, these rocks have a different texture to them. And that's because they're not basalt. They're conglomerate. That's part of an old part of the Troutdale Formation deposited by the Columbia River. So we know these rocks are older than 12 million years. And that tells us just right there, boom, the Columbia River had to have been here 12 million years ago. But there's more, because if you see these rocks, they look a little different than these rocks. And that's because they are. This is the edge of a canyon carved into the Wanapum basalt, which was the series of lavas of the Columbia River basalt that sits on top of the Grand Ronde. And so there was a canyon here in which the Columbia River flowed, deposited all these gravels. So there's a lot of stuff here at Mitchell Point. And just as a kind of to summarize that, we've got the gravels that demonstrate an antiquity for the Columbia River, and that they're being deposited in a canyon suggests that there was actually uplift going on prior to 12 million years ago, so that to cause that erosion to carve the canyon. Okay, now this is looking north up the river, and Multnomah Falls and a lot of the waterfalls are here on the south side of the river, north side of Oregon. And you can see just how steep that is. That's why there's so many waterfalls there. But on the Washington side, it's not nearly as steep. The gorge is really very asymmetric. And you can see as far here as Beacon Rock. The reason the gorge is so asymmetric is, well, at first glance, it's because the north side, the Washington side, is prone to really big landslides. This is all part of the Skamania landslide complex. It goes almost all the way to Beacon Rock. In fact, this rock out in the river here is part of that landslide complex. And the reason there's a lot more landslides too as you go up the river, but the reason it's prone to landslides is largely, well, it's because the rock is tilted gently to the south. And so here we've got the rocks tilted gently to the south. If you're on the Washington side, that's towards the river. So rocks can slide towards the river. If you're on the Oregon side, they can't slide towards the river. So you get some landsliding, but nothing nearly as big as you get on the Oregon side. And it's also is affected because of the stratigraphy, because the Columbia River basalt here in brown and then the underlying Eagle Creek Formation here are both really permeable. So water can rain and it soaks into the fractures in the basalt, and it seeps through those fractures, gets into the Eagle Creek Formation, soaks right through it, and then it pools at the top. There's an old soil developed here in the Ohanapakash Formation, and that's impermeable. So it pools there, and that kind of buoys up the rock and it facilitates landsliding. So you get these really big landslides heading towards the Columbia River. Here's a view from up on Beacon Rock looking upriver. Again, you can see the Eagle Creek Formation here is tilted gently to the south. And here's some Eagle Creek Formation. You can just see how it just kind of looks permeable. It looks like, it's lots of material in there that's pretty coarse grained. It can just kind of soak its way into it. And then it's sitting on top of the Ohanapakash Formation, which is really the onset of the Cascades volcanic arc in this part of Washington and Oregon. And here's a view of the Bonneville landslide, which is part of the Cascadia landslide complex, farther up the river. Here's the Bonneville Dam. Here's the Bridge of the Gods. And this landslide dammed the river. It was about 600 years ago, and that sparked the Bridge of the Gods story. Apparently you could walk across the river then because it flowed all the way across and dammed it. You can see how it displaced the channel to the south. But it dammed it, and it caused the lake to back up basically all the way from here all the way up to Tri-Cities. And it eventually broke through the dam and flooded downstream. Had Portland been there at the time, it would have flooded Portland to a depth of about 20 feet. So you can imagine how big that flood must have been. And that was 600 years ago. But it was nothing compared to the Ice Age floods. Here's Crown Point looking up the river again. There's Beacon Rock. And the largest of the Ice Age floods that I think, I'm a little sheepish talking about Ice Age floods to you all, seeing that you all have been following this in great detail, but it continually amazes me. The maximum flood crest was nearly 100 feet above Vista House, which is right here. And you can just imagine how huge these floods were. There were multiple floods. Just to recap how they formed, in case anybody came in here without knowing a lot about them, they formed because the Cordilleran ice sheet, as it made its way into the northern part of what's now the United States, there are these various lobes that came down. Like here's the Puget lobe here, and then this one, I think it was called the Purcell lobe. It blocked the Clark Fork in which was a river that drained northwestern Montana. Now this caused this gigantic lake to form, Glacial Lake Missoula. Now not all the floods came from Glacial Lake Missoula, but a lot of them did. And you can see just, this, if you look at the scale down here, this is 100 miles from where the glacial dam was to the city of Missoula, and it continued all the way south down the Bitterroot Valley. In fact, if you go to Missoula and look up on the hillside, you can see strand lines from Glacial Lake Missoula, and they're more than 1,000. These upper ones are more than 1,000 feet above the valley floor. So you can just imagine how huge this lake was. And when it broke through the ice dam, it coursed down through the channel, creating the channeled scablands in northeastern Washington, came down through it, got to Wallula Gap and backed up to form Lake Lewis and blasted its way through there. And then on down, there was another hydraulic dam here at Columbia Gap. It caused things to back up all the way down to Eugene and eventually out to the coast. And it happened repeatedly. There's a whole, I'm sure you guys get into this in a lot of detail, but it's amazing to me how much detail has been, the chronology here, where the first main dams went all the way down the river, and then later on, as these lobes blocked part of the drainages, that it evolved and they went in different places and so on. And so in the gorge, you start seeing really good scablands up around the Dalles. Here's some more scablands along the Columbia River. But then you go up, farther north, there are these amazing coulees. Here's Dry Falls, and here's an aerial photo out of a commercial jet from Soap Lake. Going up, Dry Falls is right here. And, there's a whole progression here where the Nick Point in the floods migrated all the way up Grand Coulee to where Dry Falls is now. And there's a similar progression here underneath Banks Lake. Bruce Bjornstad, who I guess leads you guys on field trips all the way, I hope you've seen his book. It's positively beautiful. And so, I mean, he is sort of the expert. I often referred to his stuff when I was trying to understand some of the material about the Ice Age floods. But there's just such a wealth of information and so many amazing things with these floods. Now, you know, in the Columbia Gorge, there's gravels, and the gravels are economically really important in Portland. They're mined and stuff. We've got gravels and lake bed deposits too in the Willamette Valley. One of the things we have in the Willamette Valley, and I'm out of the gorge, but I just wanted to add this, that we've got, you know, these glacial erratics, which were rafted on icebergs, and many of them were deposited along at the same elevation around the Willamette Valley, because that's where the ice kind of floated up to. This rock here at Erratic Rock Natural Site is a part of the belt supergroup, which we find in northern Montana and southern BC, and southern Alberta. And here's a map showing the Willamette Valley, and all these little dots, these little triangles are places where erratics have been located. And they're around the margins for the most part, because that's where the icebergs would have settled. I had my own little experience down here in Eugene, where my boyfriend is fond of scoping out possible trails and things like that, and he wanted to go out onto the mud flats of Fern Ridge Reservoir when they drew the water down a couple years ago. And so we put on our rubber boots and went walking out there, and we were right in this area here, and lo and behold, there were these blocks of granite, which really there's nothing that could have come from anywhere except along from one of these floods. And here's a rock that I'm pretty sure was part of looks like it's belt supergroup, and these things were right down here in the southern Willamette Valley. So they had really far-ranging consequences. So anyway, with the Columbia Gorge, we can take all these different rock units and just kind of put them in their order in which they formed and create a little cross-section here. So the early Cascades rocks are at the bottom in blue, and the Columbia River basalt here in brown. We've got Troutdale Formation in various places. Cascade Range, and boring volcanics and so on. And just to kind of make sense of it, and so these are the main topics that I wanted to address that we see in the Columbia Gorge volcanic activity that dates back to the early Cascades. The Columbia River dates back, you know, more than 12 million years. See the bedrock structure facilitates this landsliding into the gorge, towards the river, which causes the Washington side to not be so steep. And of course, then there's Ice Age floods. And if you look at the more regional cross-section, you can get a little more perspective on this, because, you know, here's the Columbia River Gorge, just sort of in a schematic way. And it really would just be somewhere in here on the cross-section, a pretty small area. And you can see that the Columbia Gorge doesn't have any of the accreted terrains exposed. It's all cover. But another thing you can see by looking at the much more regional cross-section is just how much there is. I mean, it goes on and on and on. And you know, the geologic story of the Pacific Northwest is this, you know, it's this ever expanding story, because we keep learning new things. And as we learn new things, that story gets even richer and richer, and more interesting. And as a case in point, you know, here's a view of Crater Lake, which is Oregon's only national park. It was the 5th national park in the US, I believe, something like 1903. It's one of the deepest lakes in the world. It's, I think, the 7th deepest lake in the world. It's almost 2,000 feet deep. It's incredibly clear. It formed when Mount Multnomah, which was a pretty typical Cascade volcano, erupted catastrophically 7,700 years ago and emptied its magma chamber and collapsed downwards and and now it's this beautiful lake. But if you were to go there, you and spend any time in exploring around, you'd find all sorts of nooks and crannies. And if you thought about the geology, and you'd start learning all these interesting things about it. For example, Wizard Island here is a volcano that formed within the caldera after the caldera formed. And it's actually the top of a pretty big mountain, because the lake goes down 2,000 feet. Or almost 2,000 feet. You'd find out, you'd realize that these U-shaped notches are the profiles of glacial valleys that were beheaded during the eruption. Mount Scott here goes as a satellite cone that's 420,000 years old. It's got its own history, its own detail, its own story. But Crater Lake is just a small part of the Cascade Range, which is represented as this little triangle here on the top of the cross section. It's a really small part. So the story just keeps going on. And I think that's, for me, what I find most exciting about being a geologist and learning this stuff and then writing these books and sharing it, is that it's this process where there's always going to be something new to learn, and that just never ends. So thank you.
Thank you very much. That was great. I really enjoyed that. Does anyone have any questions they would like to ask us, Dr. Miller?
Oh, Marli, please.
Sorry. Okay.
That's all right.
I have one. Marli, that was really a fascinating story you've been telling. I followed some of that before, and you filled in some gaps.
Oh, thank you.
But I'm going to be spending a week in Newport with my sister-in-law coming up from Los Angeles. And you had a couple early slides in there depicting the coastline. I wonder if I could get a copy of those.
Oh,
in your book?
Yeah, I have a website, and you could just download scads of photos. Let me, I'll share my screen again, and let me, hold on here, let me.
And I can make sure to send out your website.
Yeah, let me.
To all the members.
You guys mind if I show off my website?
Please do.
Okay, let's see. Let me first. Okay.
Incidentally, I'm a graduate of UO, so I spent a lot of time down in that region.
Oh, nice. Yeah, I love University of Washington. Oh, University of Oregon.
Oregon,
yes. I
yes.
sort of love University of Oregon too. I somehow just transposed those two.
Yeah, I would have never left it if I could have worked there.
Well, you'll stop by sometime. I swear I'm here all the time, except I'm leaving Thursday for 2 weeks. But I'm otherwise. So here is my website. It's called geologypics.com. And you can go in here, and there's a search function up here, or this red dot. There's also some galleries and things like that. But this is the main thing, the image search. So if, say, you want to look at pictures of the Oregon coast, you could type in Oregon coast and then hit reply. And I had 171 images come up. And these are all the coast. And so, like, here's an aerial of Yaquina Head by Newport. And these are all freely downloadable. You can download the image right there. So, use it to your heart's content.
Does your book,
non-commercial purposes.
Does your book cover a text about describing some of this?
Yes, actually, both Roadside Geology of Oregon has some detail on the Oregon coast. And then my new book, Oregon Rocks, has specific localities. It's got 60 specific localities around Oregon. One is Yaquina Head. That's one of the localities. Another one is Devil's Punch Bowl, just north of Newport. And then south of Newport, Yachats and Cape Perpetua. So Newport is in a really great location. I didn't cover Seal Rock because there was just too many places in that area, but Seal Rock is down there too.
Just got back from 3 days in the Prineville Bend area.
Oh, wow.
And that's fascinating geology there, but I didn't know anything about it, and I still don't know a lot, but I know what I saw.
Uh-huh. Yeah. Did you get to Smith Rock?
Oh, yes.
Yeah.
And Ogden Gorge.
Uh-huh.
I guess that's the Crooked River Gorge.
Yeah. Oh, the Ogden Skiing
Yes, Ogden Skiing Park. Yeah.
Yeah,
and
there's
I was with him. It was a great time.
We got to see something really different.
Yeah,
it's Eastern Oregon, but it's high desert. It's quite different from Columbia Basin.
Uh-huh. Well, it's funny because, I went to grad school at UW, and I never learned much about the Columbia Basin. And I remember when I was starting to write Roadside Geology Washington, I was kind of like, oh yeah, this will be easy. It's all basalt. And there's so much there. I mean, it was one of my, I think I've got the book right here. It might be the longest part of the book. Anyway. Well, you guys don't need to watch me thumbing through a book, but.
Well, I'll talk while you thumb.
340. Sorry?
I'll talk while you thumb. Go ahead. Since I've retired, I've been in Washington. I can audit any class at UW I want for $5 a credit hour. It's just practically free, and I hate to throw that faculty away. So I've been doing that, and I've exhausted a lot of their geology classes.
Oh.
But one thing that I did enjoy was one of the first ones I took, Processes of the Earth. They had a field trip, entire weekend spent over in the Eastern Washington on the Columbia River.
Was Daryl Cowan leading that trip?
Daryl Cowan and John Stone.
Okay, yeah, he took you guys to Dry Falls.
Took us to Dry Falls, took us out to Banks Lake. We camped overnight out by Banks Lake. All the way through Moses Coulee.
Okay.
And the debris field at the south end of Moses Coulee.
Oh, okay. And then you saw probably all those gigantic ripple marks across the river.
Right.
Yeah.
They really showed us a lot.
Yeah, he spoke very fondly of that field trip.
Yes.
Yeah, cool.
So, Marli, my name is Bill, and I don't have a camera, so you don't have to look at me. So you're fortunate there. But when the Earth gushes out 50,000 cubic miles of lava, locally, what does that happen locally where it comes out of all those dikes? Does it sink? Why? Seems like something should happen there when you get rid of all that underneath.
Yeah, actually, one of my colleagues, Gene Humphreys, has got all these models about what that does to the upper mantle, because it gets depleted in the in basalt, and then you get these different effects that cause, I guess, uplift in some places and subsidence in another. And I think that the whole Pasco Basin area is so deep, and partly in response to this. I see Bruce is there. He might want to add into this. You might be able to elucidate this better than I can. Maybe not. But anyway, it definitely plays a big role. And I don't quite understand what all those roles are, though. Sorry for such a bad answer.
Bruce, were you gonna add something?
Marley, I'm here. Can you hear me?
Yes.
Okay. Could you see this book,
Oh yeah, Assembling
Tumbling
California.
California? He was on NPR. They rebroadcast it on Science Friday one time. I ordered the 4 books, and they're so far over my head, I don't understand hardly anything they say. The camera's upside down.
Well,
Anyway,
now,
Assembling California. Your talk was Assembling Washington, but they're pretty good books, but
yeah,
way over my head.
I remember reading several of John McPhee's books. I enjoyed them. But sometimes, you know, if you're not too familiar with the language, he uses it, defines a word, then goes on and proceeds to use it along with 6 other terms that he just defined. So it can be kind of hard to follow.
I have a question about the feature driving west on the freeway from, say, Boardman to Portland. And at Mosier, if you look across to the Washington side, it looks like the the cliff has collapsed. And I'm wondering what was the reason for that. Is that a fault? Are you familiar with that feature?
Well, I'm not sure exactly which one you're describing. Let's see. I wonder if I.
It's at the curve right at Mosier, looking across the river to the Washington side, and it's a very abrupt cliff on the right that gives the appearance that one side to the west has collapsed.
That's what is that called?
Sounds like Coyote Wall
yeah,
or
Coyote
Catherine
Wall.
Creek. Mhm.
Yeah, and that's it. That's a head wall, I think, for a landslide. Yeah.
It was pretty dramatic. It's very, I mean, there's a lot of elevation there.
Yeah, it's a pretty cool place.
It is.
Let me just see if I. One thing I like about these books is I'm always looking things up in them. Well, that must be very impressive
that's
for everybody.
beautiful.
It's not in the index. But I think that's what it is. Because I'm misspelling coyote. But there's also, you reminded me of another feature that was what the first mistake somebody pointed out in here's Coyote Wall, page 194, that somebody that I made in the first printing of the Oregon book was that there's what looked to me like a big dike across the river on the Washington side. And somebody pointed out to me that was actually a big thrust fault. And I looked into it. They actually sent me some documentation, and it allowed me to look into it and learn more about it. And sure enough, there's a big, crazy fault zone pretty close to Coyote Wall on the Washington side too, that brings, I think, Grand Ronde Basalt up over Wanapum Basalt. But let's see, where's Coyote Wall? Coyote Wall, a prominent cliff at milepost 70, forms a landslide head wall with the Grand Ronde Basalt at its base. So yeah, landslide, if you believe this.
Thank you.
Thank you. My editor, by the way, did the indexing in both these books, and she did a great job, and I think it would have driven me crazy.
John?
Newport was mentioned earlier. My understanding from some things I've seen from publications is that before the Cascades really fully formed, the Columbia used to drain into the Pacific down near Newport.
Okay. Well, that could make sense. That because is that Wanapum Basalt? The Wanapum Basalt, some of it actually, I mean, you see it at Newport. That's what makes up the Yaquina Head and Seal Rock, and and also you see it up at Silver Falls State Park. And the idea is that those are the same flows. It's the ginkgo flow of the Wanapum. And so really it makes sense that it flowed kind of in a semi-straight direction from Silver Falls towards Newport. And, you know, as opposed to flowing north up and then down the existing Columbia and then all the way down the coast. So there seems to have been different paths to the coast prior to uplift of the Coast Range.
And that was I believe, a Steve Rydell and others publication.
Yeah, very likely. It's amazing how much those guys have figured out about the Columbia River basalt.
Well, they were young when it started, right?
They were young when they started, is that what you said?
Yeah, when it started.
Yeah, I was pretty young when I started.
Thank you.
All right. Well, thank you so much, Marli. It was fantastic having you, and hopefully we'll get to see you in person one of these days. That would be fantastic, I think.
Well, thank you. I really enjoyed this. So thanks for inviting me.
Great. Well, thank you everyone for joining us, and we'll see you next time.
All right.
Thank you.
Bye.
Goodbye.
And